I'm talking about extension of the scheme algorithm. For link polynomials. And this is meant to be kind of a continuation of the series of lectures that I previously gave, specifically what I talked last time about the Millett-Ewing notation. Okay, so I made already some remarks about this this topic then. So I give a few more details today. So I will talk about the Homefly PT polynomial. And I understand it for the purpose of these talks sufficiently well using its skin relay. So I explained this last time what this was. So you can think of the Homefly polynomial as a map from links, then let's say oriented links to a ring of polynomials with z coefficients in two variables where I allow negative powers. And last time I used z and v, but in order to conform more to the Millett-Ewing convention, I will call these variables now L and M. Now, I again emphasize the powers can be negative. So it's a ring of what is called a Laurent polynomial in variables L and M. And the polynomial satisfies then this skin relation L P of positive plus L inverse P of negative plus M P of smoothed out is equal to 0. Again, this is not just simply I exchanged Z by L and V by M, but I also the signs are different, but all this is interconvertible, so it doesn't really matter too much. So we can use the skin relation in this way, and again I emphasize what this means. So this means whenever you have a triple of links with diagrams equal except at one place, which look this way, and that way, then the polynomials of these three links are related by this relation. Okay, and this is called the skin relation. And I emphasized and explained very briefly last time that this skin relation is sufficient to calculate the polynomial using a certain recursive process. And this is what I mean by skin algorithm. Okay, so so this is the licorice millet convention. Okay. So to relate it to last time the convention that I used was V inverse P of plus minus V P of minus is equal to Z P of smooth. So this was the convention last time, and since I explained already that I had some own modifications of the Millett-Ewing algorithm, which uses this. Okay, I emphasized that in my this is Millett-Ewing. So this is the Millett-Ewing implementation, and in my version, I'm exchanging L and L inverse. It is just for the sake of my personal taste, because when I have the right-hand trefoil, I want the powers of L to be positive and not negative. But it doesn't matter too much. Anyway, so you have these conventions. For the skin relation, the skin relation can be used to calculate the polynomial, as I explained. Now I'll explain this in more details again. So here is the program for maybe I should say. I explained this, of course, last time. Also, there is also another polynomial in two variables, which is called the Kaufman polynomial, and this is similar to the skein polynomial. So sometimes I call this also the skein polynomial because it satisfies the skein relation. So anyway, the Kaufman polynomial is a similar polynomial, and as I said, Millett-Ewing had a similar program to the one for the Honfly, and I also have, and I will occasionally mention the Kaufman polynomial, but I will not discuss now the technical details too much about the Kaufman polynomial. They are similar to the one for the Honfly polynomial, just a little bit more complicated because there is an extra term and so on and so forth. So mostly I will stick to the calculation for the Honfly polynomial. And so here is planned content. I mean, so I will give some details of the Millett-Ewing algorithm. And also with my emphasizing what I changed in how I made this a little bit differently. Then I will discuss most of the time this ominous structure called the stack. And this is quite important. So I will have to explain many things because it has implications for many of the things that I say later. And the third point that I'm going to talk about, so depending on how much time I have, are the Alexander variable truncations of the Honfly polynomial. Maybe I said that this is so the T is usually the letter that is used for the Honfly, and F is used for Kaufman. And so already at this point, in order not to mess it up later, so let me say what Alexander variable means. So I said last time that I can substitute the Honfly polynomial to get the Jones polynomial and to get the Alexander polynomial. And these are two polynomials in one variable. Okay, so you can substitute the one variable in relation to the other, then you can get the Alexander polynomial from that. So these are one variable. Okay. And okay, Alexander has another equivalent version, which is due to Conway, so it's sometimes called Alexander, or Alexander Conway, or Conway Alexander polynomial. I mean, I emphasize again, this is not me, okay, so please. So the Honfly polynomial has two variables, okay, so the L and M. And the Alexander polynomial, so let's say, in order to make it easy, let me write here Conway. So the Conway polynomial of Z is P of 1Z in this convention. So you can convert from here to here, and then the problem is then you get something like square root of -1, so you get complex units and things like this. But in the convention that I used last time, you can most easily express the Conway polynomial as by you set V is equal to 1. Okay, so and this is this variable, for this reason, this variable here. So this is the variable that remains is called the Alexander variable. Okay. So So, and for this same reason, so Z more or less plays the role of M here and V plays the role of L. So for this reason, the variable M is called the Alexander variable. The variable that gives the Alexander remains in the Alexander polynomial when you substitute, and this variable is called a non-Alexander. I call it the non-Alexander variable. So this is kind of the new variable that was discovered at the time. So, and I will say something about truncations of the Hofler polynomial with respect to Alexander variable by specifying that this is now the x. In this convention, it is M. Okay. This is the variable M. And then maybe, but very unlikely, I will say something about parallelizing. So, but probably, so like the last 1.5 points of this program will remain for the next time. So I will start talking about Alexander variables, and maybe I will finish it, maybe I will not, but quite likely I will not have time to talk about parallelizing now. So I leave this, and all the other points I will leave this to the next time. So let's go to the Millett-Ewing algorithm. So I explained this. I talked about the Millett-Ewing programs last time, and I do not want to recall these details, and these details, most of these details are not relevant now. But I give a very short summary of what I said. So I explained that Millett-Ewing Millett-Ewing programs, they were designed to calculate the Hofler and the Kaufman polynomial, and they use an own notation, which I then call the Millett-Ewing notation, and I explain what this is. So this is not relevant to recall the details of that. The only thing that I want to recall about this notation is that it determines an oriented link diagram. This means it works for links for multiple components, and it is very sensitive with component orientations and things like that. Okay. And the other thing that I may occasionally need, so to keep this in mind, it does not capture. So it does not capture isolated loops. So this is the only thing that you cannot specify with the program. So if you have a diagram and then you put beside it an extra loop with no crossings, then the notation has no means to express this loop. So these extra loops, they have to be counted. This is X. So this is the Millett-Ewing notation that was developed by Millett and Ewing for their programs, and so there are these programs. And I started then last time explaining how these programs roughly work. So now give some more details about point one. So I explained that when you have this relation, so L inverse P, and then maybe let me fix also this other nomenclature, which is very common. Very often, instead of drawing all these fragments here, you simply use an index, and then you call this P plus, you call this P minus, and you call this P0. So this means a triple of diagrams, so the conflict polynomials, or let's say P of D plus, P of D minus, and P of D0. So you have a triple of diagrams which differ like this, and plus stands for positive crossings, minus stands for negative crossing, 0 stands for a smoothed out crossing. And to make this even shorter, not to write that much, I will even shorter often write for the Home-Flight polynomials of these diagrams, I write P plus, P minus, P0. Okay. So and then I explained how the skein algorithm works. So I said something like this: whenever you have a D, so let's say this is D plus, you can split it into D minus and D0. Okay, and then you can continue doing this by switching crossing. So let's say you have a crossing here, then you can switch it there, and like this. So this means this relation allows you to express the polynomial of the one as a linear combination of the polynomial of the other, and then you can continue doing this by switching other crossings. Okay, and doing Reidemeister moves or some isotopies of the diagram. Yeah, and the goal of this was at the end to arrive at the diagrams that have no crossing. This means they only have these crossingless loops like this one. Okay, so this is what I call a terminal node. And then the polynomial is obtained by summing these nodes. And of course, I said you should do it in a way that these two diagrams are simpler. Again, you must now be careful how you apply this relation so that you make the diagram simpler. So here is an example. Okay, if you have a situation which is very common, so assume that you have this. So this is something called a clasp. Yeah. So and this is a positive parallel clasp. Okay. So then you get something like this, P of D. So this is P of. So and now you can apply the skein relation here, okay, and then you get L squared minus L squared of P of. When you turn it around, the lower crossing always remains the same. Minus Lm P of when you smooth it out. So the lower crossing remains, and now this upper crossing is smoothed out, so it looks like this, and then you can simply draw it this way. Okay. And now the point is that here can be simplified. So this is now, you can simplify this by a Reidemeister 2 move. So you get minus L squared P of this minus Lm P of that. Okay, now this is an example of how you use the skein relation so that the terms that you get on the other side are terms of simpler diagrams. This has two crossings here, this has 0 crossing, this has 1 crossing. So both these diagrams have one crossing at least less than this one. Okay, and now it means that you can continue bringing it down. Of course, maybe I should say, so there are isotopy simplifications. So mostly, say, using Reidemeister moves. I mean, this is also in one of my lectures long time ago. I mean, like the first lecture maybe that I gave about computational knot theory, where I explained what are the Reidemeister moves. So Reidemeister moves are moves that transform different diagrams of the same link. Okay, and in certain cases, you can use these moves to simplify diagrams. So, for example, this is a crossing number reducing Reidemeister 2. And you can also remove these kinks. So this is a crossing number reducing Reidemeister 1. Okay, so of course, whenever you encounter diagrams that admit these type of fragments, you can always simplify them. So, okay, so you immediately get just another diagram of the same link with fewer crossings. So you do not always have to use the skein relation. When you can use an isotopy to simplify the diagram, then you can do that. Okay. So this means this, of course, is the same as that. And by using this trick that you can apply this move here, you see that you can relate the polynomial of this diagram to the two polynomials of diagrams that have fewer crossings, and then by continuously using it in this way, you can bring it down. Now, of course, you see this depends on the existence of such a thing. Okay? So if you have a diagram with a clasp, you can do that. Okay. So similarly, I mean, of course, there is no problem to do it for this one. Okay, it's just the mirrors, and you can also do it when the rotation is the other way. So this is a reverse clasp. So this is a parallel negative clasp. So when you have this clasp, you can always simplify by using such an argument. You must be careful when you smooth out a crossing here. Okay, then it doesn't look like this, but rather it looks like that. Okay, so you must be careful. Okay, the smoothing out. Okay, but then again, you can of course remove this kink, and then you always get fewer crossings. So so this method can be applied certainly when you have diagrams with clasps. Okay. So now, so this means if you have diagrams with this kind of thing, you remove all that stuff first. So this means basically you make the diagram reduced, and then if you find clasps, then you can simplify this way. Okay, so you can find a crossing so that the diagrams that you obtain on the other side are simpler, and then you can hope to go down in crossing numbers until you reach something like this. And you can use this now to calculate the polynomial for certain types of diagrams. But the problem is that these sort of fragments do not always occur. So there are diagrams that do not have clasps. Okay. And then you have to do something more global. So what kind of moves do Millett-Ewing use to simplify data? So you have first a certain family of obvious. So you have the Reidemeister 2 and the Reidemeister 1, and then they use some more subtle things like something like that. Okay, so you can see if you have a diagram, a link with this fragment, then these two crossings can still be eliminated by pulling this on the other side, and you still have two more. You have still two fewer crossings. Okay, and this now you can find them in the paper that I had talked about last time, where they described the algorithm. I think they call these fragments like the deltas or something. So you must be careful. This has nothing to do with the delta move that is introduced by Murakami and Nakanishi. For those who, I mean, don't think this is the same. So anyway, this is an isotopy of a way of simplifying without using skein relation. So this is an isotopy. Okay, these are isotopy moves. So they just simplify without that you have to apply the skein relation. Okay, and then they use. Okay, so they use what I described over there. So they use skein relation moves. So they use clasp resolution. So which is what I described here. So this is something you can call a clasp resolution. I mean, you're resolving this clasp, so the clasp is then gone. Okay, then you have simpler diagrams. So of course you can use clasp resolution, but as I explained, clasp resolution is not always sufficient. Okay, because you have diagrams that have no clasp. So you have diagrams where none of these things work. Okay? And then you have to invent some sort of a global move. Okay, so this you see this sort of moves here. They always change a portion of the diagram which has a bounded number of crossings. Okay, so you have a piece that has 4 crossings, this has 2, this has 1, 0, 2, 0. Okay, and in a clasp resolution also this has 2 crossings and it is changed to 1 and to 0. Okay, so but these moves are not enough. So if there are a certain small number but existent number of complicated diagrams where you cannot use this method to simplify the diagram. Okay, and for this you need some global moves. Okay, so this means they do not change just a fragment of the diagram that has a small number of crossings. Okay, so this moves here, so this sort of moves, you can call them local. You can call them local because they change only a small fragment, but then you need to think about how to deal with the rest. And so Millett-Ewing observed the following. I should keep this, but so let me keep it. They observed the following. So whenever you have a diagram, then there are always, I think they call them type A or type B loops, but I mean, look into their paper. So let's say I call them A loops and B loops. Okay. And A loops are crossingless circles, which are somewhere in the middle of the diagram. So you have some diagram here to start from here. Okay, and in the middle of this diagram you have, let's say, something that looks like this. Okay, and of course the crossing, so it may go above or whatever. Okay, so something like this, whatever. So a crossingless circle. So, and then there is the other one, which is you have a piece of a component which does not intersect itself between 2 passes of a crossing, and then you have, so let me do this with white. And then this lies somewhere in the middle of some more complicated diagram. I don't know. You may have something like this, and then also more components and things like that. So, and of course, this white piece, so this is a piece which is the piece of a component that passes a crossing, then does not cross the component itself until it goes until the second passing of the same crossing. Okay, now of course it can pass other components, so you will have something like that. And then this let's say this will be below, whatever, or maybe this will be above, and this will be below, something like that. Okay, so this is a type B loop, and for them, you can use the skein relation to pull them, on top or on bottom. So you see, if such a thing is below the rest of the diagram, you can always remove it. Okay, and similarly here, if it is below the rest of the diagram, it is a loop which is below the rest of the diagram or above the rest of the diagram, you can always shrink this loop. Okay, this is an isotope. You must be careful again, as I said, in the case of the A loops, that when you move this loop out, you get a crossingness loop that you have to count. Okay, but by any means, if you can put it on top or on bottom using crossing changes, then it can be simplified. So you get diagrams with fewer crossings. Okay. And the other terms that you get from the skin relation, okay, those which you obtain by smoothing out these crossing changes that you switch, they have fewer crossings also. So the strategy is, if you have something like this, you pull them on top. So this means, for example, or on bottom. So this means in this case, I fix the crossings which are below and change them. So what are the crossings that are below? This is below, this is below, this is below, this is below, and this is below. And this is below. And similarly here, so what is below? Below is, let's say, here, here, and here. So this means if you switch these crossings, then the loop can be collapsed. So when you switch these crossings, then this loop can be removed. And the terms that the terms that you get from smoothing out the crossing, they also diagrams with fewer crossings. So at the end, you can simplify these fragments by applying the skin relation at these blue crossings. So this is now more complicated, okay? There are not only two terms that you get more terms, okay? Because it depends on how many times you switch the crossing. So you get 1 plus the number of crossings that you switch terms. But the point is that they're all simpler. Okay? Of course, this can be complicated, okay? But this is now a method that allows you to do this for a general diagram without having to rely on some class or something like this. So this is now a general method that works. But so Millett-Ewing make this a little bit more they make it a little bit trickier in order to make this more efficient. So what they do is they say, when I have, let's say, when I have a loop, and I have some things here going. Let's say I have a type. Okay, let's say I have a type of B loop, or maybe it's the other way around, looking to the paper. Okay. Anyway, so if you have such a loop, okay, and I said you can switch all or where the crossings were, let's say where this is below, so that you can pull the loop out. But in fact, what they do is they say you do not need to switch all the crossings on this loop. You just need to switch as many so that the over arc becomes at least as long as half of the length of this loop. So for example, I do not need to switch the whole thing, let's say, so that it's this way. So when it is above everything else, and of course I can collapse it. But in fact, what I can do is I say I switch fewer times. So let's say I leave this here, and let's say I leave this here, and I leave this here. I switch fewer times, okay, so that this length is at least, or let's say slightly more than half of the total length. And then what I can do is I can move this thing to go this way. And then I get, instead of the white loop, I get this loop. But this loop has now fewer crossings. Okay, of course I must say that this, I'm not drawing this very well. So that of course this loop must go back very tightly along the piece of the white loop that remains, or something like that. Okay, now this, let's say now this is above, so this piece here, which is on the right, may still have some under process, but the piece which is on the left is all above. Okay, and then so the move is this white piece is moved here. Okay. And the point is that now you still have a diagram which has fewer crossings. Okay, so this is a kind of complexity thing that needs to be considered, because for complexity reasons, it is not always good to generate too many terms during this process. So if you can generate fewer terms and you can still simplify, it's usually better. And this is the reason why they do not want to do this until the end. Of course, they can switch these crossings also and then completely remove the blue loop. But it turns out if they do it this way, then this simplification may enable more efficient other simplifications in the next stage. Okay, and this is the reason why they do not want to do it until the end. Okay, because it may be faster just to simplify until here. And since this you have this very tiny, very thin fragment, I usually call this the needle. Okay, so and this is why I call this also the needle move. I don't know exactly the terminology that Millett-Ewing were using, but so they apply this type of needle moves to simplify this type of diagram. Similarly, you can do here. Okay, so now I don't want to draw it for the A loop. So and this is the reason why. So the creation of this sort of fragment is the reason why I like calling this like a skin needle algorithm. So Millett-Ewing kind of proposed this method of simplifying diagrams, and in order to be efficient, for example, they use a certain involved analysis of A loops and B loops. So whenever they have a very complicated diagrams, let's say without clasp or without deltas, they identify all the A and B moves that are possible in the diagram, and then do a complexity analysis to make an estimate of how complicated it would be to simplify this particular type of A and B loop using a needle move. Okay, and then they try to choose the A loop and the B loop that promises them the fastest simplification. Okay, so for example, one factor is how many crossings they need to switch. Okay, this is a very important factor because it determines how many terms they get. Okay, so and so what I did is, so in my version, I did this now not only for, so I did this not only for type B loops, but for a certain generalization of the type B loop. Because you see, when you want to do this kind of thing, you do not really need that these fragments meet at the crossing. It is enough if they form two edges within the same region. So if you have, let's say, something like something like this. So you have a region here, and you have a component which forms two edges in the boundary of a region. Without it, they form a crossing. Okay, and now you see this same philosophy can be used here as well. Basically, you design this B loop to have a crossing because this, you know that this type of thing will always occur. But once you implement a needle move for a type B loop, you see it almost immediately. You can do this also for this more general. General type B loop. And for example, I did not want to implement these deltas. I did not implement these deltas, but in order to have something more general, I did this also. So a more general version of this is if you have, let's say, So you have a loop which goes into the boundaries of two neighbored regions. Okay, and then you can again do this kind of thing, except that so when you make a needle, okay, you still have introduced one crossing on the edge which is between the two regions. So you have some more general versions of this needle move that I implemented, and I was using this in order to optimize. Okay. So as I explained, I said this last time, the Millett-Ewing algorithms are very fast. Okay, let's say the implementation is fast, but there are many errors, so I have to design it in some safe way. Okay, and in order to save time, I implemented this more general version of needle moves. Okay, so that I can get it at least a little bit faster. Okay, and I mean, I admit I cannot reach their speed. Okay, so I said last time, for example, when I calculate 60 crossing Kaufman polynomial, then Millett-Ewing program takes about 3 days. Okay, and I think that in my own implementation, the fastest that I was able to get it was about 6 days. Okay, so I have only half of the speed, but of course I try to rid myself of all these problems that I explained, that it crashes, that the output is unreliable, and etc. Okay, so for these reasons, I implemented also these more general types of needle moves. So this is okay, and there is one more thing. So that I mentioned here is that Millett-Ewing introduced a detector for simple diagrams. So when you do this kind of simplification, I said before, you can always reach diagrams that have no crossings, which have just isolated loops. Okay. But Millett-Ewing, so they introduced some code to detect these simple diagrams. So the diagrams of the Hauptlink and of the trefoil, so that whenever you reach a diagram that has this plus possibly isolated loops, you simply record this as a terminal node and do not resolve this trefoil further. Okay, in order to save a couple of steps of resolving it, because the effort of resolving the trefoil costs more than simply recognizing it when you have a 3-crossing diagram. So they have a special handling for terminal nodes with few crossing diagrams. So and I implemented this as well. I mean, basically I was looking into their program, and then I was trying at least to recreate as much of it as I could, because I certainly couldn't understand all the details. But so, and then then you have a terminal node count. So you obtain nodes which are of this sort. So this, or this, or this, or this, or of course you can also have the unknown. So you get terminal nodes of this type, and then you count them with their weights and contributions, and what you get is the whole polynomial. So this is how the Millett-Ewing algorithm more or less works. Okay, now I'm of course much over time, but it doesn't matter. So anyway, I'm not hurrying in explain. So this is what the Millett-Ewing algorithm does, roughly. That's my modest recreation of the algorithm so far. So these are types of terminal nodes of Millett-Ewing. So now, with great delay, I start talking about the stack. And this is truly important. So it's an important feature of the Millett-Ewing implementation. So, imagine so you understand you have a procedure that you can use the skein relation to simplify diagrams. So, and then of course, the first thing that you would do if you are to program this is to have some kind of a procedure. Let's say I use kind of close to C, let's say polynomial P of diagram D. Okay, now you start doing something, and then you would have something like this: if D is equal to loops, then return some given polynomial, and else, or let's say, okay, let's say if this something like this, then return minus L squared P of this minus LMP of that. Okay. So you design a procedure which returns the polynomial of a diagram, and if you apply the skein relation in appropriate way, then you can relate it to these two polynomials, and then you call the procedure recursively. So this is a recursive call. Okay, and I mean, of course, now you have to write a code to handle this sort of thing, etc. But at this point, only the implementation of detail is relevant. So you can, of course, write a procedure that calculates the polynomial by calling itself recursive. Okay, so and for demonstrative purposes on something like this, it's very. This is maybe the first thing that you would do. Okay. But you will very soon realize why you should not do it. Okay. And this is something that I will try to explain, okay, in the remaining 10 minutes or so. And then I will do the rest next time. So why is this not good? So why is this not good? Okay. So what happens? So what happens when you have a procedure that calls itself recursively and you run the program? So the compiler organizes something like an execution stack. So this is not only for Confluent apparently, but every time you have a program running, there is a stack of active procedures. Okay, and so let's say you have a procedure A, okay, which calls procedure B, and then you have the active procedure B, which calls procedure C. Okay, and then say from here, C, and then maybe it calls A. Okay, and then A again. So you have this stack, okay, of what are the active procedures calling each other with the state in which this call was performed. Okay, and so whenever a procedure is finished, then this is taken off the stack and you go back here and so on. Okay, so this is something which is implemented internally in the system. Okay, when you execute your program, it has nothing to do with Confluent polynomial. Okay, so every time you have this execution stack. So now what does this stack do? Okay, of course it saves you the entire data structures that are within these procedures. Okay, so now if you have something like this, let's say in a Confluent, let's say P polynomial P of diagram D. Let's say if D is equal to this, return P of that. Okay. So if you have something like this, then this is the easy case where basically you call a procedure and the compiler knows that when you determine this return value, you can also give it back to this one. Okay, and when you do something like this, then most good compilers have kind of a tail, it's called tail optimization or something. This means when you have you have your stack, okay, and you have something like that, then the compiler can simply replace it. He does not need to put this on the bottom because he knows that this procedure, once it gets this value, then he can simply go back without doing anything else, and then he can simply override the position of this procedure by that one. Okay, and then you can simply replace the pointer of the calling procedure for here, something like that. So this is I don't know about tail optimization or something. So and good compilers. I mean, this is not something that you can like direct a compiler to do, but I think if the compiler is good and it notices that you can do this kind of thing, and then in the context of Homefly, tail optimization would look something like that. Okay, this is when you have the polynomial P returned directly from a polynomial of a procedure call. Okay, but it becomes more complicated. So what happens here? Okay, here you cannot do this anymore because you have at least two recursive calls, and then of course you have to. He will start stacking. And now, what is the problem with this? There are two problems with it. So two problems. So at least. So first is memory. Of course, whenever you have a procedure on the stack, it is saved with its entire variables and the stuff. Okay, and the compiler does not check how much of it you still need later, and so on and so forth. Okay, so so this means all these procedures. So when you have these recursive calls of P, you have a lot of stuff here that is not really that may be optimized, but you cannot do this. So you cannot remove these variables from the stack because they're inside the procedures. Okay, so it copies, or it maintains a lot of memory that can be optimized. So this is the first thing. The more serious thing is the problem when you have interruption. Okay. So what happens if you run this program and at some arbitrary point this gets interrupted? As I said, these are programs that were designed to run for a very long time, so you must prepare for this situation. Okay. It is very difficult. So basically what you would have to do is you would have to create a copy of this execution stack on disk, okay, then load it from the disk and continue the execution of the program from there. Okay, this is basically what you would have to do. But this is very difficult. I mean, I do not know how to write execution stack. Maybe you know in C there is this header file longjump.h, okay, and it contains a type. It contains a type which is called jump buffer environment. Okay. And that variable, as far as I understand, is kind of, you can copy the execution stack of the program into this data type. Again, you can use it by this set jump and long jump calls to restore certain internal states of the program. So you can return to a certain execution state of the program. But I do not know how to write this on disk and how to read this from the disk. So by any means, it is very difficult to properly handle interruption if you do it this way, because usually the program itself cannot very much manipulate or even read the content of the execution stack. The execution stack is very machine system specific. Okay. And it is not supposed to be kind of manipulated by the program. There is this thing, but this is I think the only thing that I know. So interruption is a problem. If you do it this way, you want to run it over a long time, then interruption becomes a problem. If you interrupt at an arbitrary point, then it becomes very difficult to save the state of the internal execution state of the program and to restore it, then to continue from there. Okay, so these are two basic problems of doing it this way. So, and the solution to that is that Millett-Ewing so implement stack yourself. So Millett-Ewing understood that in order to overcome specifically this problem, it is much, much better to implement the stack themselves. Okay, and how this goes, I will say it in the next lecture, because now it is 1 hour is over, and I mean I wanted to say more, but it's okay. So next time I will explain how the Millett-Ewing stack works, and then I will say something about truncation and maybe interruption. Okay, so I have done much less than I wanted, but okay, it's not. I mean, I'm trying to explain something in a concise way. Okay, thank you.